Click. Okay, so this will be our permanent live lecture time, Wednesdays at 2 o'clock. They'll all be recorded and posted on the resources page. So if you miss them, you can catch up on them. And like always, I'll take the chat window. And if questions get asked there, I will answer them in a Word document and then post the PDF of that as well. So should be lots of ways to take advantage of this. But if you're here, you get to ask your own questions. Okay, so first thing I wanted to do was talk about resumes. And I know that's deep on everyone's mind these days with the really weird, wacky job market. But I want to help with that as much as I can. So if you've got skill sets on your resume, and I think most of you do, here are the things you want to add to those skill sets from this course. And I'm just going to type here into this Word document. Certainly OpenMP, because, well, hey, you're doing it now. That certainly counts. Next is going, and there's going to be multiple OpenMP projects, but after that, you're going to do something called SIMD SSE, which is single instruction multiple data. After that, we get into GPUs, and you're going to do 2 GPU projects, one in CUDA and one in OpenCL. And then for the last project, we'll use the message passing interface, MPI. And that's how clusters run, and that's how supercomputers run these days. So if you're going to accept a job and start work tomorrow, don't put any skill sets on your resume you don't actually have. But if you're looking for jobs or internships that start in June when the term's over, then I think it's perfectly legitimate to put down the skill sets you will have by then, by the time you're on the job. So if you're interested, those are the skill sets that you should write down for this class. All right, second order of business, move my windows around, is office hours have been set, and they started today. And they're on the class resources page, and they look like this. And if you, let's see if I've got it handy. Oh, I don't. All right, never mind. We did hit our goal of basically blanketing the week. Is I don't think there is any time, Monday through Friday, 8 through 6, that we don't have somebody covering. So you should be able to get all the help you need. And we're working on trying to get some evening or weekend office hours too, in addition to all of these. Notice there's 11 of us. So certainly, don't go to just one, pick several people. We all have a different style of interacting with you. Pick someone you're comfortable with and someone who's available at the times you want to be. But you have a lot of choices here, and that's what we wanted you to have. All right. So lots of things to do today. Okay, yeah, there's a note set called scripting, and I think probably it would be good if we start with that. Now, Project Zero is really an anomaly. Project Zero is an anomaly in that you're getting 2 values. You're running the program all of once, then recompile, then run it again. But that's not that hard to do by hand. In fact, I know some people are using scripts to do that, but you really can do it by hand just as easily. But the others won't be that way. The others, we might be trying maybe 5 different numbers of threads, 1, 2, 4, 6, 8. And we might be trying 10 different data set sizes. And, okay, that's like 50 trials. And so now going from the project 0, edit the program twice, run it twice, to edit the program 50 times, run it 50 times? I think not. You certainly can, and I'm sure some people will, but I value your time a lot more than that. And so what I would love it if you would do is pick up on the scripting. So yeah, right. Let's see if we can automate this. Okay, so in the code, you've seen a line that looks like this, or some lines that look like this in the project 0 code. And this pound define numt to 2, well, it is just a preprocessor command. And so when you say OMP set num threads numt, 2 would magically go in there. The compilers get very upset if you define the same thing twice. If you say pound define numt 4, then pound define numt 2, they get very upset. And so that's what this if not def is here for. If numt is not yet defined, then go ahead and define it. Okay, but if it is defined, don't redefine it. Okay, now how could it possibly be redefined, or how could it possibly be already defined? This is at the top of the program. Okay, here's how. G++, like many compilers, many command line compilers, has an option -D. Then you give it a word, equals, and a number. And from that, it magically creates a pound define numt equals whatever that number is. That's how numt could possibly be previously defined, is because we defined it in the command line of the compiler. Okay, so this is what a script would look like for this number of threads. For 1 thread, 2, 4, 6, 8, we're going to do this. And for each one of these G++ lines, it's going to pound define numt to be one of these 5. So it's a normal for loop idea. It's going to go through these commands 5 times, recompiling with that in it, and then running the program. Okay, then go to the next one, then go to the next one, and so on. This is a bash script in bash format, and you would run it by saying bash and then the name of the script. Easy. Okay, but it gets better than that. It gets way better because you can nest for loops, just like in Python, just like in C. So here's the outer for loop, the threads. Here's the inner for loop, the data set size, whatever it is we're doing. And now we've got 2 -Ds. So we're doing 2 defined constants. That's why it looks like this. So we are pound defining numt and nums. Okay. Well, now we've got 5 different thread counts to try, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different data set sizes. Well, okay, 5 times 13 is 65. That is a little big to manually edit and run the program. So yes, I really, really recommend you embrace the scripting thing. Okay, doesn't have to be bash. There's many other shells. There's C shell. So that exact same thing, here it is in bash. Bash has the cool t-shirt though. C shell, it looks like this. So you could do that. Python, it looks like this. You can do this in Python. Python kind of is half programming language, half scripting language. So if you want to treat it as a scripting language, you can. Same thing. We're going to run the G++ compiler with these -D constructs. So yes, no matter how you choose to do it, use the scripting. That's method number 1. There's another method you can use to get these variables in there from outside. Instead of making them defined constants, let's make them global variables. So a global variable called numt, a global variable called nums. We're still going to set the number of threads this way, but in the main program actually has arguments. This is the argument count. So when you type the name of the program, that counts as 1. And then any arguments, the next argument counts as 2, 3, and so on. And then this is an array of strings. argv stands for argument vector. It's an array of strings that is the name of the program. That's the bracket 0 bracket. The first argument, that's bracket 1 bracket, and so on. So if I ran the program by saying program and then put a 1 and a 64, then inside the main program, I could do this, is I could say, go to arg1. So this is 0, this is 1, this is the second one, this is 2. Go to argv1, which is the string 1. This is a built-in C function called ASCII to integer, A3. Sounds French. And that's how we set num_t. And we would set num_s by looking at argv bracket 2, doing A3. So yes, there's num_s. So you can do it this way as well. One way is you have the compiler do it. Here we put it on the command line. I'm especially mentioning this way because if you're on Windows and you want to do scripting, probably your best option is PowerShell. And there's a note set that we have in our notes called PowerShell, and it'll show you how to do it. But nothing in Windows knows about the -D, but instead we would do this. And so you would compile your program using Visual Studio, and then in PowerShell, you would use that executable and put the numbers you want to do on the command line. So yes, that's a way to do it as well. Yeah, and if you like the command line number on the command line approach, you can still do it. So in Bash, here it is. We're not doing the recompile with -D. We're putting the number on the command line. Here it is in Bash with nested for loops. We put 2 numbers on the command line. Here it is in C Shell. Here it is in Python. And so there are multiple ways to go about getting your arguments into your program so that you can just run a script and not have to manually edit and recompile a whole bunch more times. Because, that's that's pretty terrible. Okay, oops. Now what I want to do next is run a live class demonstration, which is about the scariest thing that I do in my life. It's very, very much like the trapeze artist without a net. But let me make this, I'm going to make my window text a little bigger. Okay, so I'm going to share the screen and you're going to see a big black shell window. Maybe I'll see if I can make the text even bigger. Okay, so this is actually my version of Project 1, which is the first time you'll really need to do this. So in Project 1, I have proj01.cpp. And so I have a make file. And in my make file, we'll just go through the whole process. This is what a make file looks like. This is the target. What is it I'm trying to produce? And this is what I need to produce it. And you can have more than one thing on the line, okay? So the make program, lowercase make, M-A-K-E, if you run that, it's going to go look for this. And if it finds this, then it's going to run any other lines that are there to produce the target. And so here we're not doing the -D, so it'll just default to the right number of threads. If I type make, which is a Linux command, it goes out and looks for this make file with a capital M, and it does that. It wants to make this, it needs that, it found that, and therefore it executes this, and there we go. And if I run it, oops, there I go. So there's my output. But again, I would have to do this a whole bunch more times. So if I go look at my script, here's a bash script, looks just like it did in the notes. Here we're doing numbers of threads. Here we're doing data set size. Here we're recompiling the program with the minus capital D, producing those secret pound defines, and then we're running it. So if I do this, if I say bash, hoop.bash, and by the way, this is all replicated in the project 1 lecture video. Yep, takes a little longer to run when I've got a big data set size, but there we go. And so, yeah, it's recompiling the code 60 times, but we don't care. We don't care. It's not us who's having to produce the executable, it's the compiler. So here it is for one thread and all combinations of the data set size, 2 threads, all combinations. This last column is the performances. Okay, so let's do the whole demo because there's another note set on something called pivot tables and another note set on something called graphing. Well, yeah, it's on graphing. But as long as we're here, let's do this whole thing. So I had run this before, so I need to get rid of this. All right. So why to print out number, comma, number, comma, number, comma, number? Because what that does is it is in a format called comma separated values. Okay, and comma something I wanted to change here. That's okay. We'll keep talking. And comma separated values is a known Excel format. Oh yeah, okay, we're good. So if the way that you run a script is we run it just the way we did it a moment ago, loop bash, loop.bash, except you divert it. Greater than ampersand means take all the printout that normally would have shown up on the monitor and send it to this file. So I'm going to send it to a file called proj1.csv. And notice I don't see anything because, well, it's being sent to the file. Okay, there we go. Okay, and if I look at proj01, .csv, I see exactly what we saw on the screen a moment ago. Okay, so that's nice and all, but here's going to be the real kicker for you. So let me go, I'm going to get over on Windows and go to this same folder. Okay, so now I'm over on Windows. So we're right here. And yeah, there's all my files. And there's the CSV file. And so you can see it's got a little Excel thing. That's because that comma separated variable is an Excel format. So Excel recognizes this should be an Excel format. So you don't have to copy and paste your numbers into Excel. You just have to double click on it and Excel pops up. So now I'm going to go over and just share the Excel window. And Excel pops up and has all the numbers in it, in the right columns, in the right rows. And again, so you ran your script, you output to an Excel compatible file, and you just dumped into Excel. And so now your numbers are there. Now, we need them in a table, okay? And they're not in a table here. They're sort of in just rows. We need to get them into a table. We could copy and paste those rows into the table, but there's something called pivot tables. And we have a note set on pivot table. So all this is repeated in that pivot table note set. But here's what we do. First of all, we have to tell it. We're going to insert a line and we're going to tell it what these numbers are. Oh, and this number here, we're going to get rid of that because that has nothing to do with the graphing. Okay, but we're going to put labels here. So this is the number of threads. I think in my project one code, I called this the number of trials, and we'll just call this perf for performance. Yeah, we can make these wider if we want. Okay. Again, this is all repeated in the project one video. Okay, we're going to copy this and we're going to say insert. And normally we insert stuff down here, but here we're clicking on, well, pivot table. Insert pivot table. Click. Okay, click. It opens up another sheet. And now we're going to tell it what are the dependent variables and what are the independent variables. Well, the independent variables are the numbers that you got to pick, which is number of threads and number of trials. Okay, so yeah, we'll make one of them the rows and one of them the columns. And then perf is the dependent variable. It's the thing you computed. So we're going to make that the values. Okay, so rows and columns, in English means um, independent variables, and values in English means dependent variable. So we've just dragged them. And people love pivot tables. If you've got, say, financial data and you've got tons of rows, you can be graphing this and that versus this and switch it around. Fortunately, we only have two independent variables and one dependent. Okay, that does this. And there we go. Now, for some reason, you cannot paste a pivot table into a graph, but we can sweep over the parts we care about. And notice we don't care about grand totals. You would if it was financial data. Oh, profit for the months, for 12 months, add them all up. But adding up performance numbers makes no sense. So we'll sweep across everything that's not a grand total, do a copy, click down here, do a paste. There we are. We don't really need to know row labels, so we'll get rid of that. All right, so in the project handouts beyond project zero, it'd say put in a table. Well, here you go. Copy, paste into the Word document. There's your table. But let's do the graphs. So I'm going to copy that whole thing, copy, and I'm going to do an insert. And I'm going to go to the graphs, and I like the scatter plots, and I like this one with the smooth curves. Click, I'll click there, and gosh, graph. So I went from gathering all my data to sucking it right into a spreadsheet to building a table to drawing a graph. Well, if I hadn't been yakking the whole time, I would have gone to about 2 minutes. Okay. Or you can do it in 2 hours without the scripting and all of this other stuff. Your choice. Now, we need two graphs actually, because this one is we're graphing performance in the y-axis, and the x-axis is data set size, and the colored curves are thread numbers. Yeah, so no 8 threads, better performance. Good deal. But we also want to do one where the threads are on the x-axis. So we're going to copy this graph and we're going to right click on the border and click on select data and tell it to switch the rows and the columns. Done. These are the two graphs you're going to produce for all the performance-based projects. Number of threads on one axis with data set size as colored curves and data set size on the x-axis with number of threads as colored curves. Notice Excel tries to center everything on the axis, but if you right click on the axis here, like I'm trying to do, nope, that's not it. there's a format axis, and you can tell it, don't start at minus number, start at 0, don't end at 2 million, end or 2.5 million, end at 2 million. All right, now the graph or now the curves fill up the graph. And you can do the same thing. No point starting at 0, no point ending at 9. Again, Excel tries to balance your graph in there, even if it doesn't make sense. But there you go. Okay. Program, script, Excel, pivot table, graphing. Now, what I like to do is I like to copy each graph and paste it into PowerPoint, and then use PowerPoint to put labels on the axes and things like that. And then copy and paste out of PowerPoint into your Word document. But this is really all there is to it if you want to automate. Okay, question in the chat. Does it matter if we're running on your own machine? Not a bit. And really, you don't have to do this workflow at all if you don't want to. What I care is that you have good scientifically literate results, tables, and graphs in your PDF, and how you get there is up to you. But yeah, you have to get there, and I don't care where you run it. So yeah, run it on your machine if you can get it to run there. All right, any questions on the whole script pivot table graph thing? And once you get used to this, I think you're going to like it. It is really fun, just kind of blowing through all of that so quickly. Um, would you still need to change the chart titles in Excel? Yeah, well, if nothing else, you need to get rid of it. So yes, you could put in here if you wanted, click in here in the chart title and instead put performance versus data set size or something like that. What I like to do is just get rid of the chart title, then copy and paste the whole graph over to PowerPoint, and then add the chart title over there. Because then I can put it anywhere I want. I can make it colors, different fonts, and so on. But your point is well taken. Somehow, things like the chart title have to show up in your in what you're submitting, and Excel will do it, or here will do it. PowerPoint would do it. Yeah, Excel will also let you put text on your axes. What does each axis represent? But again, I like doing that in PowerPoint better just because you can move the text around and change it. However you get there is up to you. I only care that you do. All right, other questions so far? So this whole workflow is covered in the Project 1 video labeled LV in that row in the project table. And we have notes on graphing, pivot tables, scripting. So all of that information is there. All right, so there isn't a syllabus quiz. Well, there is a weekly quiz. Um, that's correct. Let's see. I don't know what a syllabus quiz is. But there is a weekly quiz. You'll get on it on Canvas. There's every week there's a quiz. Um, oh well, okay. Tell you what, let's do that. Okay, so if one were to go over to Canvas, and this is my view of the class on Canvas, which I'm sure is different from your view of the class on Canvas. But if I go to any one of the sections on parallel programming. And if I go down to week 1, and this is going to be true for every week, here's all the notes, here's all the projects, and here is quiz 1, the quiz for week 1, and it tells you it's going to open on April 5th, which is Friday. All the quizzes open on Friday, 1 minute after midnight, and all the quizzes close 1 minute till midnight. Okay, and so after it's opened, if when you click on quiz 1 after it's been opened, then it'll go right to the quiz. But it's not going to do that right now because, well, it's not been opened. And quiz number 1 is super easy. You have nothing to worry about. The quizzes, by the way, are open notes. And Canvas tells me that in past years, the average person took 8 minutes to take the quiz, but you've got 60 minutes to take it in. So yes, the quizzes are meant to be not stressful. Okay, other questions so far? Is Linux Flip required? No. You can do, yeah, okay. A question is, can you do it on Windows with a GPU? You can do a lot of it on Windows with a GPU. In the CUDA project, CUDA is an NVIDIA only product. So if you've got Windows with an NVIDIA GPU, you're fine. You can do it there. If you have Windows with an Intel GPU or an AMD GPU, then you're going to have to be on one of our systems to do it. Okay, that's the one exception. The second exception is the last project, which is Message Passing Interface, MPI. That's using clusters or supercomputers. I'm assuming nobody's got a cluster at home. If you do, let me know. I'd like an account on it. But assuming you don't, then you're going to have to do Project 7 on our system here because we do have a cluster. Okay, but in general, all the others can be done on Windows machines with GPUs. And you won't need the GPUs till the CUDA and OpenCL projects. If you don't have a GPU locally, you must use OSU servers. Yes. Now, one of those is Rabbit, so which a lot of you have been using anyway. And we have a very big, bad multi-GPU system. We have a mini supercomputer of GPUs, which you'll get to use. It has 96 NVIDIA cards in it. You're going to get to use one. So, but it's still a great card. Like it's got about 10 times the performance of the GPU that's in Rabbit. So you'll get some phenomenal numbers. So even if you've got a GPU at home, you might want to try it on our DGX system here, just because you will probably just get some astronomical numbers, which are very cool to tell your friends about. Okay, does that answer the questions okay about where you can and can't run programs? In general, we want you to run them on your own system if you want, because it is cool to check out what your own performance is. All right, any other questions to this point? All right, let's move on. So there is a note set called parallel background. And parallel background is, well, they're sort of loose topics that really needed to be talked about in this class, but I couldn't think of sort of where to put them. So I collected them all here. So if it looks like they're disjoint, yeah, it's probably because they are a little disjoint. But here we go. All right. So 3 reasons to study parallel programming. These are 3 reasons people use it. One is to increase performance and do more work in the same amount of time. So let's say you're a data analytics company and you're analyzing 1 million credit card records. but now you want to analyze 2 million credit card records, but you don't want it to take any longer. Okay, that's a really good use for parallelism. More work, same execution time. Number two is increased performance. Same amount of work, less time. This is sort of the game programming model. In game interaction, you have a 60th of a second time slice to get everything done for that frame of the video. And if you take less time doing one thing, that gives you more time to do something else. And then number three, make some programming tasks more convenient to implement. That's called functional decomposition, and you'll do that in project two. Okay. A perfect example of that is a web browser. When you download a web page, it's extracting images from other web browsers or other web servers. And if one of those web servers is really slow and bogged down, the whole loading of that web page doesn't freeze, just the loading of that one image. Well, that's because your web browser puts the loading of things on different threads. So each thread can run independently, and if one thread is extra slow, it doesn't slow down the whole loading of the web page. So yes, multi-threading sometimes makes tasks more convenient to implement. So yeah, so the first kind of parallelism, like one and two here, is called data level parallelism, meaning same equation, different data. And so, for instance, when we break up a for loop with OpenMP, it's essentially breaking it up to 1/3 of it goes to one thread, the middle 1/3 goes to a second thread, the final third goes to another thread. Essentially, that's what it's doing. Okay, that's data level parallelism. The second, or the number three here, is called functional or task parallelism or thread parallelism. Each thread is doing something different, some different part of the process, and this way they can all work together without having to wait for each other. Okay, so most of the things we'll do in this class, the projects are data parallelism, but project two is functional. This is something called Flynn's taxonomy, which we don't really need, but I included it here because I've been told by some students this is an interview question. Hey, explain Flynn's taxonomy. It has to do with how many data values get processed per how many instructions. A normal single core machine like we all had 10, 15 years ago would be SysD. I think that's how you would say that. Single instruction, single data. Each assembly instruction does one thing to a piece of data. We're going to get to SIMD, single instruction, multiple data. And the one we're going to use, and you'll do a project 4 on this, is for every instruction you execute, 4 pairs of numbers have arithmetic done on them. That's cool. You'll like that. And then MIMD is sort of like multiple cores, multiple threads running independently. And MISD, well, that would say multiple instructions, single data. The only thing I've ever heard that is like that is there are fail-safe computers, like the space shuttle, when it was running, had 3 computers on it. And so that if 2 of them disagreed, the third one would break the tie. That would be considered multiple instruction, single data. In general, we don't worry about it. Okay, architecture. John von Neumann was one of the pioneers of computer architecture. This was back in the 1950s, 1960s, and this was his setup. There'd be an arithmetic logic unit. That's who does the add, subtract, multiply, divide. There was an accumulator there to put numbers in. There was a control unit to handle things like looping and if statements. And there was memory. Okay, this is basically our same architecture today. Now, it's bigger, it's badder. Instead of accumulators, we have 20 registers sitting out there, but the idea is still the same, except we've added, well, registers. There's a program counter, which is an address that shows what's the next instruction in your program to be executed. And then there's a stack pointer. And the stack is used for things like local variables, function call arguments, the return address from the function. And so what you realize is if we're going to do multi-threading, then each thread has to have its own version of these. Each thread has to have its own registers, its own program counter, and its own stack pointer, or the threads can't run independently. And so that's true. And so multi-core architectures are essentially the John von Neumann architecture from years ago, plus all of these. Okay. Um, Now, if you've been in OS1, you know about processes, but processes is something running on the computer. Each thread is actually a process. It's a special process in that the multiple threads are sharing an executable, and the multiple threads have their own registers, program counter, and stack pointer. But each thread really is a process. And so that gives you a sense that in the same way that it takes an operating system a little bit of time to spin up a process, it takes the operating system a little bit of time to spin up a thread. So there is overhead in using OpenMP. Yeah, a thread is an independent path through your program. All right, but let's go to here. When the world went from single-threaded programming to multi-threaded programming, well, what did they have to change? So these are maps of memory. Well, here's the program executable for one thread. Here's the program executable for multiple threads. Same thing, because each thread shares the same executable, just maybe taking different paths through it. Here's the global variables in a one-threaded world. Well, here's the global variables in a multi-threaded world. All the threads share those as well. Here's the heap. malloc, new, it's dynamic memory allocation. All the threads share the same heap. So they are all processes. They're just special processes because they share so much in common. Where it gets different, where memory gets different is right here. One thread, you only need one stack. Each thread needs its own stack. And so they take the big stack space and they divide it up into smaller stack spaces. And each thread gets its own. Okay, but as you can see, it's not all that different from the single threaded programming era, except we can do more with it. All right, we don't have to go to all of this. There's some definitions here that I threw in. Yeah, be sure to look at that. I'm not going to go over them now. We'll talk about them when we encounter them. All right. The second part of this is parallel programming tips. And the reason we're doing this is because there are times when OpenMP will screw up and not say a word. Okay, there are certain things you shouldn't do if you're doing multiple threads. But OpenMP doesn't flag those. It doesn't say, no, 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 don't do this. It just lets it go. This is part of your value added. Remember, I like to say parallel programming at all is easy, doing it well is tricky. This is part of your value added, is to know these things and don't do them or spot them in other programs. Okay, so here's tip number one. Don't keep internal state. Now, what does that mean? Normally in a function, local variables are on the stack. And the moment the function returns, all the stack variables go away. But if you add a local variable and you put the word static in front of it, it becomes permanent. It persists between running of that function. And a lot of things are written that way. Yeah, sometimes it's handy. Have the function remember where it left off so it can resume there. Great. This is great in a single threaded world. But now you have threads sharing the code, but there's not multiple versions of that variable. They're all writing into the same variable. And that's where the problem happens. And ironically, where this happens a lot is in built-in C functions, like the string handling. So here's strtoke. Stir_toke is a built-in C function that takes a big long string of words or commands separated by commas or blanks, and it gives you the first one, and then you call it again, and it gives you the second one. You call it again, it gives you the third one. It's really useful for parsing commands. Okay, here's where the problem comes in. So thread number one calls stir_toke. It gives it the line of things it's parsing, the commands. And the way stir_toke works is it puts this in a static variable, and then you call it multiple times again. And here you call it with null, and that means pick up where you left off. So you give it a big long string of multiple subcommands, and every time you call it with null, it just goes down to the next one, to the next one, to the next one, and gives it back to you. Okay, along comes the multi-threaded world. Here's thread one. It calls stir_toke. It gives it this. Now that internal variable is pointing into this string somewhere. Now thread two comes along, calls stir_toke with a different string to parse. Well, that internal variable is now pointing into this string. So the next time thread one calls stir_toke, it's going to be getting things out of line number two, which, that it's kind of weird when this kind of thing happens, is you're asking it, you're printing out what tokens it's finding in this line of tokens, but it's printing out tokens that appeared in this line. That's because of the internal state. Okay. Now, how do you get around that? One is some systems, and I think Visual Studio has this. I don't think G++ does, but there's another stir_toke underbar R. The R stands for reentrant. Reentrant means another thread can go back in after another thread has already been there. What this does is it keeps the information on where did it leave off in an external variable. So here is how you'd use it. You'd call stir_toke R, same two arguments, and then you pass back the return value. And then when you call it again, you pass the return value back in. And so there's a difference. Where did I leave off for thread one than there is for thread two? And that solves the problem. But this is something you've got to look for. And by the way, it doesn't have to be internal state. Keeping a global variable is just as dangerous. Anything that both threads can write into differently is going to be dangerous. And OpenMP doesn't do anything to keep you from doing it. You just have to know. All right, tip number two, avoid deadlock. Deadlock is when two threads are waiting for each other to do something. Thread 0 is waiting for 1 to do something, but 1 is waiting for 0 to do something. And this is something nobody ever does this on purpose. This is something you do by accident. But the scheduler in OpenMP is non-deterministic. You and I have no control over what order the threads execute in. Okay, and so a multi-threaded program might run for a minute, for an hour, for a day, for a week, for a month, for months, and all of a sudden come to a halt because the threads are waiting on each other. Okay, again, this isn't something OpenMP will help you with. It's up to you to be looking for that. Race conditions. This is really important. So it's called a race condition because it matters which thread gets there first. So let's say we're pushing and popping. So in CS261, you all learned about pushing on a stack, popping from the stack. The push code looks like this. You increment the pointer and then put the incoming value at the new pointer. Popping, you take the outgoing value off the stack and then decrement the pointer. Okay, what happens if we've got a thread? So maybe we've written this application. Thread one is gathering data from somewhere and pushing it on the stack. Thread 2 is popping it on from the stack and doing something with it. So what if thread 1 executes P++ and then the scheduler comes in, swaps out thread 1, brings in thread 2? Well, now thread 2 is going to pop something off the stack that's not really there. It's using the wrong P, and it's going to decrement the P. And so by the time thread 1 picks up, P is all wrong. Okay, so the stack is going to get garbled. This is not good. Now, what do you do about this? First trick is recognizing it. Second trick is trying to fix it. What you do about this, when we get to the full OpenMP notes, we'll talk more about mutexes. But a mutex stands for mutual exclusion lock. And you put a mutex around this code, and you put a mutex with the same name around this code. And OpenMP adds into the compiler code that says if one of the threads is inside this mutex area, the other one's not allowed to enter until the first one gets out. So that means that thread A would get to do both of these before thread A or thread 2 got to do either one. Okay, so that's called mutexes. Volatile. In the single threaded world, what if we had programmed this? We set the value to 0, and then we have a while loop that says keep looping as long as the value is non-zero. Well, in a single threaded world, that's not possible because, well, we set the value to 0, it's 0 here, and that while loop will kick out right away. Okay, and because of that, a good compiler will take this line and get rid of it. Okay, it'll just get rid of it because it knows val is 0. Well, okay, along comes multi-threading, and another thread could be changing the value of val without the first thread's knowledge. And so in that case, this would be a perfectly legitimate line of code, but not if the compilers removed it. So the way you solve this is you put the word volatile in front of int val. Volatile means it can be changed often in the background. And so now the compiler, even optimizing, would know not to get rid of this line, that this line actually could happen. Suddenly the value of val could change on the fly. And when we talk about caching, we're going to talk about something called false sharing. And this is an example that we'll do in the caching notes. So this blue line is the performance when run with one thread. And I normalized everything. So it's not absolute performance numbers. It's relative to the one thread performance. Now we go to two threads. Two threads is this red curve. And notice we go to two threads and the performance gets worse. The performance goes down. You think you're doing multi-threading and you are doing multi-threading, but the performance goes down. Okay, something is not right here. And it's this thing called false sharing, and we'll talk about it in the caching notes. Notice going to 4 threads, the green curve made it even worse. Oh yeah, let's add more compute power to it and lose performance. This will make sense when we get to cache. Okay, so that's the end of this catch-all area called parallel programming background. Let's see, any questions? Oh, okay, one left over from before. Most of the projects are run on the CPU, not the GPU. That is correct. We're not going to get into GPU projects until CUDA and OpenCL, and those are the only two that will use the GPU. And there is no final project in this class, so you don't have to worry about that. So yes, that's what you say is correct. All right, any questions on anything up till right now? All right. And what I'd like to do next is start in on the deep dive into OpenMP. So we looked at the simple OpenMP notes that made sense. I wanted to give you enough on Monday that you could get started on project number 0. And many of you have. I checked the teach turn-in area this morning, and about a sixth of the class had finished and turned in project 0 already. So that's great. And that's a measure of, well, it's project 0. It's not meant to be very involved. It's just a feeble excuse to get you into OpenMP. But now it's time to go into OpenMP in more detail. All right, OpenMP. The MP stands for multi-processing. It's open because it's multi-vendor. It's not something that Intel concocted and is forcing on the industry. It was a bunch of vendors got together and said, we need to do multi-threading, multi-processing, but we want a standard way to do it. And what they came up with was OpenMP. And OpenMP is both compiler directed and library based. So there are OpenMP functions. OpenMP set number of threads is one of them. And compiler directive, that's the pound pragmas, which tells you something about it, is the way OpenMP works is all the compiler writers, got together with the OpenMP spec and they injected OpenMP producing code into the compiler. So when G++ runs on your code, if you've got OpenMP directives in there, it's going to add code to do those things. It'll add code to spin up threads. That's kind of cool, as it's built into all those compilers. The threads share a single executable, a single set of global memory values, and a single heap. Each thread has its own stack. Each thread, or the threads really require no dramatic code changes, which is what I really like about OpenMP, is if it's something you want to experiment with, you can add OpenMP into your code really pretty easily. Okay, and so, yeah, that's what we're doing. Pragma OMP parallel 4, and off we go.
I'm sorry, Mike. We
Whoop,
cannot see any slides.
up. Oh, you're right. Thank you. Well, good. We only got this far. Oops. Yeah. Okay. Thank you. Okay. Let's see. Actually, let me share it. Up, up. All right. Now it should be okay. Ah, thank you. Okay. This is important because here's what OpenMP does not do. First of all, it doesn't check for things that it's going to mess up on, like data dependent. And we'll talk about these things, but things like race conditions, that push and pop example, it doesn't flag that. That's up to you. That's part of your value added. I can get a grade school kid to type pragma OMP parallel 4, but it's you and your computer science education that knows what these things are and knows to look for them or knows not to do them. Okay, so we'll talk about what these are, like data dependencies. It doesn't check for non-conforming code. It wants your for loop in a very specific format in order for it to work. It doesn't check to see if it's in that format or not. It just messes up if it's not. It doesn't guarantee identical behavior. Like if you run your OpenMP code on your home system and then you go run it on Flip, it doesn't guarantee identical behavior between those two. And in fact, it doesn't guarantee identical behavior if you run it twice in a row on Flip. Okay, because the scheduler is on its own schedule. And you and I have no control over the scheduler. And for instance, if we spin up 8 threads, thread 0, there's nothing significant about thread number 0. It doesn't get to go first because it's number 0. 8 threads get spun up, and it's up to the scheduler. The scheduler decides who gets to go first, who gets to go second. So you will not get identical behavior. Most of the time, we don't care because, for instance, when OpenMP is dividing up your for loop, all we care is that all values get computed. We don't care what order they get computed in. Just by the time the for loop's over, everybody got computed. But if you do care about, like, things have to happen in a certain order, well, you have to do things a little differently. OpenMP is not overhead free. There is operating system overhead in creating the processors or the processes that are the threads, which tells you that OpenMP should not be used when you have small data set sizes. That is, the overhead is going to swamp any advantage you get from doing multiprocessing. And OpenMP does not prevent you from, well, getting that false sharing. In fact, OpenMP makes it easier for you to get that wicked false sharing. And we'll talk about that in the caching notes. Okay, we talked about this. Really, the big difference is the stack. Each thread has a stack. Other than that, it sees the memory arrangement the same way it would have if it was not doing threading. And we've seen this. This was in the simple notes. By the way, I oftentimes repeat things like this because I want every note set to be standalone. It would really make me angry if the note set consisted of a lot of, oh, go look at this note set. It's over there. So yes, you've seen this before. Yep. If you've got OpenMP turned on, then this underbar OpenMP is pound defined already. And so here we're asking, is this defined? And if it is, we're going to print something nice. And if it's not, we're going to print something nasty. If you get this message, what that usually means is you did not turn it on. That is, you on G++, you forgot to do this, minus F OpenMP, or in Visual Studio, you forgot to do this. Any system you're on right now should be capable of having OpenMP turned on. So if you get this message, check to make sure you've turned it on. Okay, these are some of the functions that OpenMP has. This one we're going to use a lot, set number of threads. Now it doesn't create the threads right then and there. What it does is it just records the number. And so next time you ask for threads, pragma, OMP, parallel, it'll create that number. Okay, and there's some query things you can run as well. Like if multiple threads are running, well, which one am I? So think of it this way. I kind of think of it in terms of the Ben-Hur chariot races, is you say pragma OMP, you call that function set num threads, and then you say pragma OMP parallel. And anything that begins with those 3 words is going to create the thread team, the number that you asked for. So up until then, 1 thread is going through your program. Right after that, 4 threads or 8 threads or something are running in here and executing all those lines. Okay, 1 horse becomes 4 horses. Yeah, so this isn't 4. This is just any code you put in there. The pragmas operate on the next line of code or the next block. If you've got more than 1 line of code you want them to operate on, then you put the curly braces around them. So whatever I put in here, all threads are going to execute that code. Okay, so I tried this. I set the number of threads to 8, pragma OMP parallel, and then I put a printf in there. And for the number it's going to print, I said, just go get the thread number. So every single thread executes this line of code. I ran it several times in a row, and this is what I got. This is the non-deterministic scheduler thing. Here 0 went last, here 0 went first. There's no rhyme or reason. And if we ran it another 20 times, we'd probably get 20 different orders. Okay, so this is what you expect, and this is what we accept in using threading packages, is the scheduler is in charge. Okay, but if we say pragma OMP parallel, we get multiple threads. But if we say for, that's really special because that says apply the multiple threads to divvying up the for loop. And that for loop has to be right after pragma OMP parallel. Okay, you can't say pragma OMP parallel up here and then have a for loop a bunch of lines of code later. It wants to figure it out right away. Okay, and this is probably the most common use of OpenMP is to do things in for loops. That's that data level parallelism. Now, OpenMP has rules for the for loops. Okay, you say pragma OMP parallel for, then you've got the for loop. And the for loop, the format is you've got an index variable and a start value. You use the index variable in a terminate condition, I less than 100, say, and then you change the index variable, I equals I plus 1. Okay, the index must be an int or a pointer. In C, in normal C, it can be a float, but not with OpenMP. If you try and parallelize a for loop with a float, it might work, it might not. Second bullet, the start and terminate conditions must have compatible types. That is, if I'm using an integer here, then I have to do an integer comparison there. Okay. Bullet 3, the start and the terminate can't be changed. So if I've got I equals 0, and if here I say I equals I plus 1, that's fine. But if in the body of the for loop I say I equals I plus 10, that's going to mess everything up. And here's why. If you think about this from the point of view of what if you were the compiler, what would you do? What the compiler wants to do is look at this line of code, the for loop, and generate all the divvying up stuff right then and there. Okay? It doesn't want to look down through what your code is. It wants to look just at this one line of code, and from the information given, break up the for loop. Okay, so if you play with the index in the middle of the block of code, that's going to goof it up because now when you get back here and you say I equals I plus 1, well, if down here you said I equals I plus 10, really now you're adding 11. But OpenMP thinks you're only adding 1. Okay, it wants to look at that one line of 4, and from all that information, generate all the divvying up that needs to be generated. Okay, you can't use a break or a go-to to get out of the loop. We all do that all the time, right? If some condition happens, break out of the for loop. Can't do it here because what does that mean? What does it mean if one thread does a break and the others don't? This one is really important, okay? Make sure that this one makes sense to you. Interloop dependencies. Now, we do this all the time in normal one-threaded C programming. Let's say we want to fill the array with 0, 1, 2, 3, 4, 5. Well, we do that. We just put the first value in, and then we say in the for loop, a of I equals ai minus 1 plus 1. And that's known as an interloop data dependency. But here's why that is dastardly. Let's say that we're doing this. And so, yeah, we do 100 through the for loop, and we get to this line, and we get to this line. But what if the way that the for loop was divvied up, the lines above the black line went with thread 0, and the lines of code below the black line went with thread 1. Okay, this line of code right here is the last thing that thread 0 is going to do, because thread 0 has all the stuff above that. This is the last thing that it gets to do before it's done. This line of code is the first thing that thread 1 gets to do because it's in charge of everything below that. Well, when thread 1 executes this line of code, it's going to expect that a value exists for A101. But A101 is not actually going to get produced until the end of thread 0's run. Okay, so when A102 gets produced, there's garbage here. So you can't do this. And this is something we all do all the time, but it breaks the threading model. If you absolutely positively need to do that, then do that, but don't put it in a Pragma OMP parallel 4 because something is not going to behave correctly. Okay. Okay. Any questions so far on what OpenMP will or won't do and what it's demanding of you? Let's see. Yep, that is exactly right. Mhm. Okay, so let's see. What version of G++ does Flip use? By default, I think it's still using 4.8.5. It comes with the version. I'll tell you what, I can just go find out. You can find out if you say G++ space minus version, it will tell you, oh, okay, it's 11.4. All right, it is 11.4. Okay, it's been updated. It used to be 4.8.5. Anyway, you can always find out G++ minus version. G++ is actually up to version 13. And every year I ask the IT people to load the latest version. So it's out there somewhere. User local something. The version 13 is out there if you care. Let's see. Why do we think 1 thread and 4 threads should be less than 4? Yeah, basically think about your experience with perpetual motion machines. Okay. Why does some machine not have 100% efficiency? Well, in the mechanics world, there's friction. There's things that don't contribute to the running of the machine, like friction. And in a parallel program, there's things that don't contribute to the parallelization of the program. Like in Project Zero, the setting up of the for loop, there's assembly code that was generated that sets up the for loop, but that has nothing to do with computing the values. This part of the code computed the values. This part of the code did the setting up of the for loop. Okay, so think of that part of the code of setting up of the for loop as the friction that's in your Project Zero code. Yep, you're right. Yep, I'll go change that in the simple OpenMP. They're not out of date. That one thing is out of date. I worked on those like in the last month, but I will fix that. Yeah, it's nice. It's nice. They must have updated the Red Hat version um, that runs on Flip. And G++ of a standard version, it comes with Red Hat. That's why even if G++ has newer versions, the Red Hat has the older version. All right. Any questions on things that OpenMP will do or not do, or things to look out for? Because that's really the important thing right here. This is your value added to this, is your knowledge is what's required to make sure bad things don't happen. Okay, there's also some restrictions on what you can do This is the only thing you can do for setting up the index, like int I equals 0. But typically that's what we all do anyway. This is the only thing you can do for testing the termination. Sometimes we test termination with not equals. Go as long as I not equal to 0. Can't use not equals. And these are the only options for changing the index. Okay, sometimes we multiply by 2. Index equals 2 times index. Not here. So again, OpenMP has a certain expectation of your for loop because it needs to use just the information there to figure out how things will get divvied up. Okay, now here's a question. If I say float x equal to 0 and then I go into the pragma multi-thread for loop, and now I use x down here, is x common to all threads, or does each thread have its own x? That is, if I assign it here, what does x equal? Does it equal I for whatever the last thread to get to that line is? Or does each thread have its very own x? And there's no good way to guess at it. And so you have to tell it. And so out on here, out past 4, there's other information. And one of them is a list of variables that every thread is supposed to have its own copy of. And those are called private. Any variable defined inside the for loop is automatically private. Okay, so I is considered inside the for loop, it's private. Y is private. Every thread is going to get its own very own Y. So they're not colliding. If I say private X in this pragma line, then I'm going to get every thread gets its own private value of X. If I say shared X, then they're going to share the value of X. Okay, but you make that call. You know what's supposed to go on. There is a default, and I don't even remember what the default is. I can go look it up. But the point is, you should always set these deliberately. Don't rely on the default. And so to do that, you'll see in the sample code, I always put default none right here. And what that means is it turns off whatever the default is. And then OpenMP, this is one of the few things OpenMP will complain about. If you have variables in use inside the for loop that were defined or declared before the for loop, and if you say default none, it will complain that you didn't declare them private or shared. And that's a good thing. That's a good thing that it doesn't use the default and quietly say nothing. Okay, so you'll see default none. It's optional, but it's really recommended. Okay, now we already know that this kind of interloop dependency is not allowed. Okay, but this is parallelizable. So what do you do in a case like this, where you've got one line of code that you can't use parallel for and one that you can? Well, you break it into 2 for loops, and that's called for loop fission. Is we go ahead and handle this without OpenMP, and we handle this one with OpenMP. So sometimes you've got a for loop that you programmed up in a one-thread world, and some of it can be used and some can't, but you just break it into 2 separate for loops. If you absolutely need to do this interloop dependency, you really have no choice, but simply don't turn on the multi-threading. What about this? You've got 2 nested for loops. This one's going to go around n times. This will go around m times. So together they're going to go through this code n times m times. Where do you put the pragma? The answer is OpenMP will fix this for you. Is rather than trying to guess, do I put the pragma here? Do I put it there? You put it outside and you say collapse. So the code that it generates will actually collapse these two into one for loop. You won't see it. You'll program it the way you meant, with one for loop on the outside, one for loop on the inside, but internally, it'll work like you want it to do. Okay, there's another way of doing the parallel programming besides the for loop called single program multiple data, which which gets pronounced as SPIMD. Yeah, we have to pronounce everything. And it works like this. Okay, here's the number of threads. We've already declared how many threads we want. Pragma OMP parallel, not for, just parallel. And so now all threads are executing these two lines of code. Each thread is going to get its own value of me. Okay, so that should have been declared int on the inside. But each thread is going to get its own value of me, and then it's going to call this, and it's going to pass in the total number of threads and which one am I? Okay, so all threads in the thread team are going to execute this function. And so here, whichever one you are, that's going to tell you what the first element of the data is that you need to work on. This will tell you what the last one is, and then you'll work on just those numbers. Okay, we're going to see some examples coming up later where this is a more convenient way to program. Okay, but basically you're creating a thread team, and then the thread teams are asking, who am I? And from that, they're figuring out what part of the problem belongs to them. And that's called SPIMD, or single program multiple data. Okay, this is the last thing I wanted to cover today. So we've talked about OpenMP will take your for loops and divvy them up. But how does it divvy them up? How do it needs to be intelligent about this, right? Like, what if, for instance, the problem you're solving, thread 0 has very little work to do, or I equals 0. Let's do that. I equals 0 in the for loops has very little work to do. I equals 1 has a little bit of work to do. I equals 2 has a little more. I equals 1,000 has a lot of work to do. Okay, if we divide it all up into big chunks, like we give the first fourth of the I's to one thread, well, that thread has very little to do. It's got the easy ones. The last thread has all the hard ones. It has a lot to do, which means that thread 0 is going to go idle pretty early in this whole process. Well, that's a real waste, right? Why should thread 0 get to go idle? If you could, what you really want is you want all threads to finish at the same time. That way you've applied as much computation power to your problem as you possibly could. Okay, it knows that. OpenMP knows that, and it takes that into account about how it allocates things. So in the scheduling of for loop iterations, there's something called static and there's something called dynamic. Static means that it decides at runtime, like when your program runs and it encounters that for loop, it divvies up the passes into the threads right then and there. Okay. Dynamic means it divvies up most of the threads right then and there, but it saves a few in a pool. And the first thread to go idle gets some of the pool, and the next thread to go idle gets some of the pool. And so that way, it almost doesn't matter what the distribution is. You've got enough threads left over that whoever finishes first can still keep working. Okay. So OpenMP scheduling, this goes on the Pragma line. So you might say default none and private X and all that. And beyond that, you say schedule. And you either say static or dynamic, and you say chunk size. And if you don't do this at all, there's decent defaults. But let's say that we decide to do that. So Pragma OMP parallel for default none, private or shared something, schedule, static, and a chunk size. And let's say we have 12. Let's say we have 12 for loop passes, okay? And let's say that we have 3 threads. The default is static comma 1. And what 1 means, I think of it as dogs playing poker. Okay, when the dealer dog is dealing the cards, well, deals 1 card to 1 player, another card to another player, another card to another player, and so on. That's what's going on here. So index equals 0 goes to thread 0. Index equals 1 goes to thread 1. Index equals 2 goes to thread 2. Index equals 3 goes to 0. 4 goes to 1. 5 goes to 2, and so on. The dealer is dealing 1 card to each player. Okay? And this is the default if you don't say anything about scheduling or about chunk size, because that way, if there is this really uneven distribution of work to be done, well, each thread gets some easy ones and some harder ones. And so the goal is the threads all finish about the same time. And this is probably the best way you could get that. So this is the default, or you can say static comma 1 for yourself. If you say chunk size equals 2, well, then thread 1 gets 2 for loop passes, 0 and 1. Thread 1 gets 2 and 3, 4 and 5, 6 and 7, and so on. Okay, if you know something special about the distribution of work in the for loop, you might do this, or 4. First thread gets 4 for loop passes, and so on. So these are things OpenMP does or attempts to do for you, is attempts to give you the best sort of distribution of work over the threads. But like everything else, it's up to you to know. And so you, the smart computer scientist, know something about the code and so can manipulate the scheduling to try and take advantage of what you know about the code. Okay. Yeah, well, let's see what comes. We'll cover that next week. Okay, any questions on anything we've done today? Oh, okay, static work allocation. Imagine you are the compiler and you're working in conjunction with your partner OpenMP. And you, the compiler, come down and you see a Pragma OMP parallel 4, and then you see a for loop. Okay. In a static allocation, at that time, and you know the number of threads. So in a static allocation, at that very moment, each thread is going to get its proportional share of the for loop passes. Now, so in this case, in the case on this page, we've got 12 for loop passes and 3 threads. Each thread will get 4. Here it's getting 1 set of 4. Here it's getting a different set of 4, but each thread gets each thread gets 4. And so in static allocation, it divides them up as evenly as it can the moment it sees the for statement and fires off the threads. Okay. In dynamic, it allocates most of the for loop passes to the threads, but it keeps some in reserve. And the moment one of the threads goes idle, it's generated code to give that idle thread some of the remaining for loop passes. See, it's all the idea that you don't want any thread finishing before the others, because then that's wasted compute time. Sort of like you've got 3 assistants. Well, if one of them finishes early, then the whole set of tasks could have gotten finished early if only that one that finished early hadn't finished early. So the same thing's going on here. Dynamic means it allocates not all of them, but some of the for loop passes, most of them, and then hold some in reserve to give to any thread that goes idle. Okay, and so the idea is you try and keep threads from ever being idle. You really want to try and get all the threads to finish together at the same time. Oh, okay. Yeah, SIMD slide. And actually, let me do this because we have a note set coming up on SIMD. And a project. Your project 4 is a SIMD project. Okay. So without totally barging into a future note set, let's talk about what SIMD is all about. So Moore's law says you can put more transistors on a CPU chip every 2 years. One of the things they did with that is they built hardware that could do more than two or more than one floating point operation at a time, and integer operations too. And so normally we think of Z equals X times Y. That's one multiply and one instruction that creates the multiply. But imagine this, imagine we had two arrays. Yeah, so this is what we normally do. We multiply two numbers and put it away. But imagine we had hardware that could do this, is we could have four numbers and four numbers, and we had hardware that could multiply four pairs of numbers simultaneously. That's what SIMD is. One instruction, four pieces of data. In an assembly language, it would look like this, but diagrammatically, it would look like this, is four numbers get multiplied by four other numbers, and the results get all stored away. So if you're multiplying two arrays together, this is great. Instead of going through the array one pair of numbers at a time, you're going through the array four pairs of numbers at a time. And yeah, when you do this, well, you're going to see what kind of speed up you get. But if you're guessing a 4 times speed up, yeah, you're pretty close. Okay, does that help? Does that help on the SIMD thing? Yeah, this is very cool. And the amazing thing to me about SIMD is nobody seems to know it's there. It's been there for years. Intel originally put in SIMD to try and handle audio streaming. You know how long that's been. Um, but almost nobody knows it's there, but it's like a free factor of 4. Okay, question in the chat. How would you know how to improve your thread allocation? Some of it is you look at it and you say, oh, okay, thread 0 only has to do one thing, but thread 1 has to do two things, and thread 3 has to do two things, and the number of things that need to be done go up with the index of the for loop pass. So if you look at your own code and say, well, that's what my algorithm demands, then you know that the later for loop passes are going to be far busier than the earlier ones. And that means you certainly want to do a chunk size of 1, and maybe you even want to try a dynamic allocation. If there's no reason to do dynamic allocation, then you probably shouldn't do it because there's some code overhead with doing the dynamic allocation logic. But if you think there's a really wide disparity in how much time each for loop pass is going to take, well, that's when you certainly want to use a chunk size of 1. So one card gets dealt out to all players, and maybe play around with dynamic scheduling. Largely, we just experiment with it as we go, I think this is going to require dynamic scheduling. And so we do it with static chunk size of 1, then do it with dynamic chunk size of 1, and see if we were right. Did dynamic actually speed it up because the threads were kept busier? But again, this is you, the computer scientist, using your domain knowledge. And that's why companies don't hire middle schoolers to type in pragmas. What was the default thread allocation? It's static, comma 1. Yeah, it's static with a chunk size of 1. They probably made it static because that's faster for OpenMP to take care of. There is some logic that has to go into the code with dynamic allocation, and chunk size of 1 because if there is a disparity as you go up in for loop passes, chunk sizes of 1 will try and even that out. All right, other questions from today. Um, yeah, good question. So the question in the next question, what would be a reason for ever using a higher chunk size? Um, I've never had a reason, but I can envision some. Like, supposing you were analyzing um, oh, maybe you were analyzing an audio wave, things that were sequential data. There might be an advantage into the same thread looking at several values in a row, several for loop passes in a row, because it needs to know about the adjacent data values. I'm I'm making that up. Let's see. What if you have three threads and every three threads? Oh, every third thread takes a long time. Huh. Let's see. So 0 and 1 aren't bad, and 3 is big, and 4 and 5 aren't bad. I guess I don't know. Maybe you'd want, let's see. So if you did a chunk size of 1, well, if you did a chunk size of 1, let's see. So, and you had 3 threads. Okay. Then that means this thread number 2 would always get the bad ones. What if you did a chunk size of 4? No, maybe a chunk size. I think I would try a chunk size of 2. I'm guessing. I'm guessing. But basically, you want to even it out. You don't want to do, if it's every third thread is, or every third for loop pass is the hard one, then you don't want to do a chunk size of 1 because thread number 2, the third thread, will always get the hard one. But if you did a chunk size of 2, then sometimes thread 1 would get the hard one. Sometimes that's what I would try, is I would try an offset. Yeah, it may not be, 2 may not be the right number, the right guess, but I wouldn't do 1. I guess you could do 3. Yeah, right. If you could do a chunk size of 3, because then each thread gets easy, easy, hard, easy, easy, hard, easy, easy, hard. Okay, yeah, okay. I think a chunk size of 3 would work if you knew. But again, this is you. This is your value added. This is you, the computer scientist, looking at the algorithm you're programming and saying, ah, I know something about this, and I know how to manipulate the allocation of the threads to really take advantage of the parallelism. All right, good discussion. All right, anything else? And I think that is enough for today. Let's see. We will stop the recording. Click.